The dedication now is that I choose my core or my iron core based on what? This is the idea. The idea is that engineer, the dipoles inside or the number of dipoles inside vary depending on each ferromagnetic material. All right, I have something constant for me. What is this thing? This thing tells me, engineer, that there is something called the magnetization curve, and this depends on your core. The magnetization curve, which depends on your core. All right. So what does this magnetization curve tell you? It tells you that your CT, which you have drawn, consists of what? It consists of a primary. And if I want to represent an equivalent circuit for my current transformer, it consists of a resistance and a reactance. We call them R primary and L primary. And the core itself starts with your current, which creates a magnetic field. The magnetic field begins to transfer from the primary to the secondary through an iron core, right? Am I wrong? Very good. So part of this magnetic field is converted into eddy current losses. And there's another part used for magnetizing the dipoles. So you have two branches here. One we call the R eddy, also which are the eddy currents, and the other is the RM of the iron core and the iron core as well. Very good, beautiful, okay? And in the end, on the other side, I have the R secondary and the L secondary. So of course, when the primary current flows here, it transforms into the secondary current here. Additionally, such as for instance, in particular, specifically as an example, in this case, notably, especially, moreover, furthermore, in addition, to elaborate, to clarify, to explain further, to illustrate, to provide more detail, to give more context, to expand on this, to further explain. Is that clear? Good. Regarding my transformation, and part of the magnetic field transforms into eddy currents, and another part is used where? It is used in the magnetization of the core, meaning the magnetization of the core aligns the dipoles inside the core so that it starts moving from the primary to the secondary circuit. This is also related to the concept because I also like to... This is the topic of core magnetization itself, which involves the currents being drawn here. Additionally, this is the reason why the 1000 amperes here do not transform into 1 ampere. Instead, they transform into a point, for example. Let's assume something like this. If it is 1000 to 1, for instance, it doesn't transform into 1, but rather into this value. Why? Because part of your magnetic field goes into magnetizing your core. Additionally, part of it generates eddy currents within the core, which do not transfer to the other side. This, of course, causes what is known as ratio error. That's why one of the manufacturers I was sitting with before also told me that if your current transformer, for example, has a ratio of 1000 to 1, in reality, if there's one turn on the other side, it won't be 1000 turns. On the contrary, sometimes they make the number of turns either more or less depending on your needs, like making it 1000. And 1 turns, meaning they add an extra turn, so that in the end it results in 1 ampere. Surely they apply a factor to this matter. The important thing, the idea now is not forgetting that this is the current flowing, and here you have the one connected to your device, which is the... Here the idea is quite simple. As the primary current increases, the secondary current naturally increases as well, right? That's great. So where's the idea here? Let's focus on this core. Now, as an engineer, when you connect your load, which is your burden, all right, what happens next is that as current flows here, current also flows on the secondary side. This current on the secondary side itself generates a magnetic field, and this magnetic field opposes the original magnetic field. This is what ultimately leads to the subtraction of the two, reaching a state known as steady state, right? Such that a voltage appears on your secondary side, and this voltage equals the secondary current multiplied by the total resistance. All right, and I will still talk about these parts in more detail. This voltage that appears here, engineer, is what we refer to as V. The more the current you have here increases, the more this voltage increases. As the current here increases, this voltage increases. Of course, this means that as this voltage increases, the eddy currents and the magnetization currents also increase. So it was said that we found a relationship that governs what happens with the current, whether it's your current or another current. We found that this thing behaves linearly up to a certain point, and then it starts to stabilize in this manner. This part is referred to as the linear part, meaning it is directly proportional. Then after that, I find that the quality remains constant. What does this mean, engineer? It means we found that there is something called the magnetization curve. The magnetization curve, I found that in the current transformer, whenever a current passes through the primary, a larger current is encountered in the secondary. Based on this, the voltage difference generated here in the secondary increases, assuming of course that the burden is a constant resistance and the secondary resistance of the CT and the secondary inductance of the CT are constant. So you have this voltage here continuously increasing. The more this voltage increases here, the more the drawn current increases, and the more this increases, the more it continues to increase, and so on, until we reached a certain point. This point is called the knee point, which means the bend. After that, we found the killer. We found that as you increase the secondary current, the voltage appearing on the secondary increases by 10%. We find that the magnetization current and its counterpart increase by 50%, or the current increase by 50%. This means that this is the point after which, if you come, the voltage does not increase more than this. And you find that the magnetization current, what happens to it, means that as more current passes through the primary, the more the losses here increase significantly, while no current goes to the secondary. What does it mean that no current goes to the secondary? It means I will find that my characteristics, or the sinusoidal wave, for example, if this is the primary current, the one in blue, I will find that the secondary current increases with me according to the ratio, for example, until it reaches a stage where the quality here cannot increase more than this, which is the knee point area. As soon as it reaches this stage, it means that there are no more, or what happens is that all these dipoles have been arranged. You no longer have dipoles to arrange, so you don't have dFE dt. What happens is that no flux is transferred from the primary to the secondary, so you find that the current increases like this, then decreases back to zero, and then in the secondary, it increases again like this, then decreases back to zero. So here, this shape means that distortion has occurred. Distortion, of course, distortion of the sinusoidal wave, or deformation of your sinusoidal wave, right? Nice and deep. The idea here is that as the current increases, as we agreed, the primary current increases, the magnetic field or the flux here increases, so the dipoles get more aligned and so on. We keep increasing until we reach the saturation point. That's the idea here. In the metering core, I want the saturation point to appear early. What does it mean to want it to appear early? It means I want my saturation curve to be a low curve, something like this, a low curve. Why? Because I want my core, which will have a load connected to it. And this load is a neutral device, and the meter device is not concerned with reading high currents. It is concerned with reading currents up to an overload of 150% to 200% from the rated current. Therefore, it is important for me that this core reaches its saturation, meaning all its dipoles are aligned and complete for me at around 200% of the inflow load value, peaceful from the value of the inflow, while in protection, I need my curve, which is the magnetization curve, to be high. I need to have many dipoles so that not all of them reach saturation quickly, or reach it at a specific time. When does total saturation occur? At multiple of current 20 times, 30 times, 40 times. Why? To allow the protection to work properly. What does that mean? Now, or let's say I have a protection device that will operate, for example, at overcurrent at 5 times the current, and at another overcurrent at 10 times the current. I'll give you an example. At 5 times, it is supposed to trip after 3 seconds, and at 10 times, it is supposed to trip after 100 milliseconds, as an example. Anyone who has studied protection knows this. Of course, I'm not saying it's simple. This doesn't happen. It's very basic, but let me give a simple example. Here, it's not a wand. If the current transformer enters saturation, and for example, the current value is at 11 times, for instance, the current at 11 times reaches the steel saturation stage. All right, or let's say 8 times to be precise. At 8 times the current, the steel reaches the saturation stage, causing distortion. This distortion means your sinusoidal wave is no longer a sinusoidal wave. So, is the RMS of this wave the same as if it were a complete sinusoidal wave? Certainly not. Consequently, the current might be 8 times, but due to this distortion, the relay might interpret it as 5 times or 4 times. So the relay trips after a long time delay, while in reality, it should have tripped after a shorter time delay. That's why in the protection core, I need to reach this saturation stage at a high multiple of current, whereas in metering, I want to reach this saturation stage at a lower multiple of current. So here I need my magnetization curve in the case of the metering core to be low and the magnetization curve in the case of the protection core to be high. That's nice, guys. So this is simply the difference between the the metering core and the protection core. Now, I will talk in more detail about the metering core and the protection core. I'm telling you now that for the protection core, it is manufactured from silicon steel and it has a high saturation flux, meaning the saturation stage occurs when all these dipoles are aligned or interact with the magnetic flux at a high flux density, meaning the magnetic field density must be very high to allow the passage of high currents to reach the protection device. Based on the value of these currents, it will determine which zone of protection it is currently operating on. Of course, I gave you a simple example with overcurrent, but you also have differential distance and distance protection, which includes zones of protection, and you have directional errors above with a very large set of protection mechanisms, functions, and each protection function is different from another protection function. Meanwhile, the metering core, for example, is made from something called sabica, which tends to have a low saturation point or reaches saturation at a low magnetic field density. All right, so here you have a high knee point and a low knee point. The high knee point is connected to protection devices, while the low knee point is connected to metering devices, whether analog or digital, as we agreed. Now, there's something additional here. What is it? Now, regarding metering and protection, what about accuracy? The idea is quite simple. The word accuracy means it can read with what level of error, how accurate it is, and what the error is compared to the actual value. What is the actual value? Well, the metering device reads the currents, the load, and the overload conditions accurately. In order to calculate bills, to see the amount of energy that has been dispatched from my feeder between stations, between countries, between cities, and so on. Therefore, I need to have higher accuracy. The accuracy must be very high or very good. So is protection not concerned with the concept of accuracy? No, of course it is concerned, but not to the same degree as metering. Why? Because protection relies on high thresholds anyway. And these high thresholds are levels, meaning I won't tell you, for example, that at 3 times the current it will trip at this point. And at 3.1 times it will trip at that point. No, at 3 times the current, then the next level might be 8 times the current, and the level after that, 15 times the current. So there are levels and protections that are far apart. Even if the accuracy isn't very strong, it doesn't really matter much for these large currents. However, I still maintain a good level of accuracy. So here in the metering core, there are classes 0.1, 0.2, 0.5, class 1, 3, 5, and the most common are 0.1, 0.2, 0.5. We will learn what these are, and we will read these 2 plates. Also, for the protection core, you have 5B10, 5B20, class TPS, TPS, class TX. In my experience with PST, it's Bravo PST,